Last time, we ended with building up to the idea that you can look at the structure of a molecule and you can have a good idea of which portions have high energy reactive electrons and which portions have low energy empty orbitals. You're going to see throughout this class that all the action happens, all the chemistry happens at the frontier between high energy filled orbitals and low energy empty orbitals. That's where the magic happens. And so we want to be able to look at the structure of a molecule and identify the highest energy electrons, or the HOMO, and the lowest energy empty orbital where electrons could go, the LUMO. We talked about that last time with this molecule formaldehyde. We walked through it saying, okay, you got a couple of carbon-hydrogen sigma bonds, you got a carbon-oxygen sigma bond, you have an oxygen-carbon pi bond, you got two lone pairs. We've already discussed how sigma bonds are more stable than pi bonds because sigma bonds are held closer to the nucleus. So we expect the sigma bonding orbitals to be the lowest in energy, and we expect the carbon-oxygen pi bonding orbital to be higher because the electrons in a pi bonding orbital are held higher from the nucleus. That sounds familiar? Somebody once told me that people love hearing things they already know. It helps them feel smart. So that's why we're doing this at the beginning, to help you feel like you're on the same page. Now, the pi electrons in this case aren't the highest energy electrons because you have lone pairs on the oxygen and they are not involved in a bond, right? So anything that's a lone pair is going to be higher in energy than anything that's in a bond. So that's why we put the lone pair electrons here along this dotted line, which represents the average energy for an orbital that's not involved in a bond. And then above that line, we basically see a reflection of what's below it. The carbon-oxygen pi star is lower in energy than the carbon-oxygen and carbon-hydrogen sigma stars. And you fill the bonding orbitals in the lone pairs. You keep the anti-bonding orbitals empty. If you want to check yourself, you can confirm you got the same number of electrons in this diagram as you have in this Lewis structure. But the conclusion you make is that the highest energy electrons are the lone pair, and the lowest energy electrons is the carbon-oxygen pi star. We said if this molecule is going to act as a Lewis base or a nucleophile, the HOMO electrons are going to be the ones that do the attacking. Just to review the definition, a nucleophile is, or a Lewis base is, an electron donor, by which we mean a sharer of electrons, not a here, take this electron away from me kind of thing, but a sharer of electrons. What does it want to share electrons with? A low energy empty orbital somewhere. So if you're thinking about a molecule acting as a nucleophile, always look for the highest occupied molecular orbital, always look for the highest energy electrons. If this molecule formaldehyde were going to be a nucleophile, it would attack an empty orbital on, and I'm going to be as generic as possible here, E plus just means electrophile. That means a molecule with a low energy empty orbital. This is how you would draw it, from the lone pair pointing towards whatever the electrophile is. Now, if formaldehyde were going to act as an electrophile, what we would care about for the LUMO is the lowest energy empty orbital. We're going to want to know where that is. An electrophile is a Lewis acid or electron acceptor, probably better said electron sharer. A Lewis acid can accept electrons to be shared from a nucleophile. An electrophile has a low energy empty orbital that's willing to share electrons with the nucleophile. And so we're looking for that LUMO. In this case, it's the carbon-oxygen pi star. Now last time I drew that for you, and here is that drawing again. The carbon-oxygen pi star looks like this. Here is the plane of the carbon-oxygen, carbon-hydrogen sigma bonds. The pi star, like a pi orbital, goes above and below the plane of the sigma bonds. But unlike the pi orbital, the pi star has a node along this line in between the two nuclei. And this is therefore an anti-bonding orbital. And I thought I would just show you in the program Spartan a three-dimensional view of what this pi star looks like. Here is that molecule formaldehyde. You can see the carbon, hydrogen, and carbon oxygen sigma bonds all forming a plane. That carbon in the middle, what is its hybridization? Got to be sp2, right? So I'll show you the orbitals associated with this. This is the pi bonding orbital. That's what it looks like. The two different colors there are just like the pink and the orange on my drawing. They represent opposite wave function, amplitude, or sign. And electrons in that pi bond hover above and below the plane of the page. This is the view from the top down. This is the view from the side. If we look at the LUMO, that's what the pi star looks like. You can see here is again the sigma bonds, and above the plane of the sigma bonds and below the plane of the sigma bonds, you've got orbital. You've got a node right in between the carbon and the oxygen. And the calculation shows you quantitatively what I showed you qualitatively. The LUMO is just a little bit bigger on carbon than it is on the oxygen. You can just accept that as a result. You don't need to understand why it's that way. But this is what the LUMO looks like for a carbon-oxygen bond. Questions about that, or what it means, or how to draw it? Why do we care? We care about empty orbitals because for the electrophile, that's where the attack is going to happen. And if you can identify the empty orbital that gets attacked, you also, by definition, know what happens next. This is a pi star antibonding orbital. If you filled it with electrons, you have to break the corresponding pi bond. So going back to our drawing here, I showed some generic nucleophile, assuming it's got a high energy lone pair of electrons. It's going to attack the pi star. What that would mean, based on our drawing here and our picture here, is that nucleophile has to approach from either above or below the plane of the carbon, oxygen, and carbon hydrogen sigma bonds. It can't attack from the side, always from above or below, because that's where the LUMO is. And when it attacks that LUMO, because you're filling an antibonding orbital, you have to break a bond, so you need a second arrow. So this arrow means these lone pair electrons are being shared with this carbon by being dumped into the pi star. This arrow means dumping electrons into the pi star breaks the pi bond, and these electrons move out onto the oxygen. Okay? And those arrows tell us what to predict for the product of this reaction. Here is the new bond between the nucleophile and carbon. By the way, that carbon that used to be sp2 hybridized, what hybridization is it now? sp3, because now it's bonded to 4 things, right? And then the oxygen, which used to have 2 lone pairs, now has 3 with a negative formal charge. And two of those lone pair electrons came from the carbon-oxygen pi bond. So if you know about HOMO and LUMO, you can predict how unfamiliar molecules react, and you can understand how reactions happen. And that's key to understanding all of the chemistry that's going on inside of you that's keeping you alive. One question we could ask at this point, that LUMO that we just drew, the pi star, is on both the carbon and the oxygen. But I drew the nucleophile attacking the carbon and not the oxygen. What's my justification for that? Go ahead.
Because the oxygen is, the electrons in that bond move more towards the oxygen. Oxygen is more electronegative.
Good. So you know the oxygen's more electronegative. You know the electrons in the pi bond are leaning towards the oxygen. That should make the carbon more electron poor. So it makes sense that something that has high energy electrons should be attracted to the more electron poor atom. That's great. The other thing is what I told you, that the LUMO is a little bit bigger on the carbon than it is on the oxygen. The final thing that you can use to remember that is to pay attention to the fact that molecules like formaldehyde have a resonance structure that looks like this. In the formaldehyde resonance structure, I take the pi electrons in the carbon-oxygen pi bond, I move them out onto the oxygen, and I leave the carbon with a positive charge. Now that's, I got that resonance structure simply by doing this arrow here, moving the pi electrons out onto the oxygen. This is a valid resonance structure. The carbon doesn't have an octet, so it's not the best resonance structure. Nevertheless, it does, we would call it a minor contributor, but it does give you an important piece of predictive information, which is, it confirms everything you've said so far. The carbon in the carbon-oxygen double bond is electron poor. Okay, so you got electronegativity of oxygen, you got the resonance structure, you got the LUMO lobe is larger on carbon, all reasons why that pi star gets attacked on carbon. Questions about that? Okay, yeah. So we did, and I sent you, we didn't quite get to this on the quiz last time, but hopefully you had a chance to work on this. I had you identify the HOMO of an alkene. That's a carbon-carbon. An alkene is another word for a carbon-carbon double bond. If you see a carbon-carbon pi bond, the HOMO is going to be the carbon-carbon pi bonding orbital. This is what it looks like with a lobe above the plane of the sigma bonds and below. This is the side view. This is the top view. Do you want to see it in Spartan? Would that help to see it 3D? Okay. We'll go back here. Let's just turn that into a carbon. Download. Yep, boom. All right, so we'll turn off the orbital. That's the carbon-carbon pi bond. This is the overhead view, and this is the side view. You can see those carbons are trigonal planar, Sp2 hybridized. If we turn on the highest occupied molecular orbital, you see that it's above and below the plane of the sigma bonds with a node in the plane of the page. Understand that the electrons in that pi bonding orbital, it's not that one's on one side and the other's on the other side. It's not that they're both on one side and then the next second they hop to the other side. It is that the electrons are a wave. They simultaneously occupy both sides and they go through zero in the middle. Okay? This is what the LUMO of a pi star looks like. That looks a lot like a carbon-oxygen pi star. Okay? All right. And then we just went through and I showed you what the LUMO is of a carbon-oxygen pi bond containing molecule. All right, so your quick rule of thumb when trying to evaluate HOMO and LUMO, start by looking for lone pairs. Lone pairs are higher in energy than pi bonds, so if you can find lone pairs, you've found the HOMO. If there's not, then look for pi bonds. Similarly with the LUMO, start by looking for pi star antibonding orbitals, especially between carbon and oxygen. And if you can't find that, there's a couple others that you can look for that we'll talk about. More questions on that? Yeah.
So like in that question it says draw the appropriate orbitals. Do you want us to be able to draw it from like the bird's eye view as well? No.
I want you to be able to draw multiple views. I don't particularly care about that, but you need to be good enough at 3D reasoning that if I draw it in a view that you're not expecting, you can still understand it. Yeah?
I guess lone pairs would always be HOMO, never LUMO.
Right, lone pair's always occupied, so it can't ever be the LUMO. Yep, good. Others? Yeah.
How would you draw the molecular orbital for a lone pair? Just
Great question. Yeah, how do you draw the molecular orbital for a lone pair? Let's go back to the notebook page where I'll have a little bit more space. So yeah, let's think about that for the carbonyl. You expect this oxygen to be what hybridized? Sp2, because it's surrounded by three things, right? The carbon and the two lone pairs. Its p orbital is participating in the pi bond, so what's left are three sp2 orbitals, one of which makes the sigma bond. The other two hold the lone pair. You want to draw what that looks like, you would simply draw an sp2 hybridized orbital, which has a large lobe here and then a tiny lobe there, and half the time people forget the tiny lobe on the other side, and I don't care if you do either. They make these, some people draw these as what they call rabbit ears orbitals. They, oh, it looks like a cute bunny. It's a stretch, I know, but that's how people draw an sp2 hybridized orbital that holds a lone pair. Yep. Okay, good. Good question. Others? For the most part, I don't bother drawing the orbital because the two dots remind me that it's the lone pairs anyway. Okay. So we've talked about most of the things you'll encounter in the class as nucleophiles. They're either going to be things with pi bonds, particularly carbon-carbon pi bonds, or they will be things with lone pairs. We've only dealt with one kind of electrophile that you'll see in the class, and that's a carbon-oxygen, a carbonyl, or a molecule with a carbon-oxygen double bond. There are two other kinds of low energy empty orbitals that you need to be aware of. And our goal here is not to prepare you to answer impossible questions. As I tell you about these, somebody's going to want to ask, what if I'm in a molecule that has more than one of these, and which one is the LUMO, and how do I know? The answer is really going to be, often if you have a molecule that has more than one of these kinds of empty orbitals, it likely can react in multiple ways. There's tons of molecules in OChem that are that way. You just want a good feel for how each particular arrangement of atoms can react. And we'll say more about that in a little bit. But two other kinds of low energy empty orbitals relate to bonds between let's see, halides, which I'm abbreviating as X, nitrogen or oxygen, and acidic hydrogens. What do I mean by acidic hydrogens? Stay tuned on that, because we're going to learn about that probably tomorrow. So just put an asterisk on what an acidic hydrogen is, but I'll give you a hint. One example is the hydrogen in hydronium, H3O+. So sigma bonds between a halide and, or between an electronegative element, sigma bonds between an electronegative heteroatom and an acidic hydrogen generally have low energy sigma star antibonding orbitals. Let me give you an example of that. Here is HCl, that is hydrochloric acid. And in HCl, you've just got one sigma bond, so HCl is really easy, right? It's got one sigma bond, one sigma star, and then three lone pairs. If you had to pick the HOMO of HCl, you'd pick the lone pairs. If you had to pick the LUMO, it would have to be, by definition, the hydrogen chloride sigma star. Let me just draw briefly what that hydrogen chloride sigma star looks like. It has a node in between hydrogen and chlorine. It has one lobe on the hydrogen, but mostly pointing away from where the chloride is. It has a tiny lobe on the chloride pointing towards the node, and that lobe is opposite in sign to this one. You can tell that it has to be that way because this is a node. This is a place where wave function equals 0. And then on the backside of the chloride, there's another lobe, and again, it's opposite to the pink, and you can tell that it should be because we go through a node at chloride as well. I don't usually draw the node at chloride. I do draw the node in between. You don't have to draw the node as long as the color is correct. This is a sigma star antibonding orbital. Okay. Let's just predict what might happen here. What do you know about chlorine's electronegativity relative to hydrogen? More, right? So you expect the chlorine to be somewhat electron rich and the hydrogen to be somewhat electron poor. because chlorine is more electronegative. I need an abbreviation for electronegative than hydrogen. So if I had some nucleophile with high energy electrons, I might predict I would attack the hydrogen and break the sigma bond. Okay? In so doing, at the end of this reaction, I would form a new bond between the nucleophile and the hydrogen, and I would break the bond between hydrogen and chlorine. Do you see how that works? The only empty orbital in HCl, the only thing that can accept electrons, is the hydrogen chloride sigma star. And when you fill that sigma star antibonding orbital by having the nucleophile attack the hydrogen, attack the sigma star at hydrogen, you must, by definition, break the sigma bond. So chloro takes those electrons and leaves. Okay? Questions? Yeah.
Is that why it'd be so high? That's why it'd be higher in energy because the probability of this happening would release a lot of energy?
So high in energy, tell me more about that.
On the scale when you draw it, you said like the pi stars are pretty high up.
The pi stars are high in energy, and it's only the lone pairs that are close enough to get there. Yeah, good. Yeah, the question is, does this give you a sense for how favorable a reaction is? And yes, it does, in the sense that you need the highest energy electrons to reach those higher energy empty orbitals. Yeah.
Okay, so the N here just represents
This represents a generic nucleophile, and the two dots and the negative charge just say, hey, this thing is really electron rich, and that lone pair is the HOMO of the nucleophile, whatever it is.
and so then it goes and it kind of kicks out chlorine and bonds with the hydrogen and kicks donates the bond between those two donates the lone pairs.
Okay, can you say that one more time because I missed it? A little bit louder.
So what's happening here is it that the generic nucleophile attacks, you said it attacks the hydrogen? Or-
Yes, the generic nucleophile attacks the sigma star antibonding orbital on hydrogen.
Okay. And then when that happens, it breaks the bond?
It makes a new nucleophile hydrogen bond, which is what this arrow means, and simultaneously breaks the hydrogen chlorine bond. Yep, and that's a good rule of thumb. Anytime you fill an antibonding orbital, you make a new bond, but you break the old one. Yeah.
Why again does it choose to attack hydrogen versus?
Why does it choose hydrogen versus chlorine? Chlorine's more electronegative than hydrogen, so the electrons in the hydrogen-chlorine bond are leaning towards the chlorine. The hydrogen's electron poor. It makes sense for the high-energy electrons to go to the atom that's least electron-rich, most electron-poor. Yeah.
Since those new electrons from the nucleophile are filling in on the hydrogen, on the LUMO position, would the electrons then be in the sigma star orbital, or would they?
Yeah, it's a good question. We're showing these electrons from the nucleophile donating into the sigma star. What we're not drawing for you is what happens in the middle and then afterwards. And you can draw orbital pictures for what the middle is like and what the aftermath is like. We simply haven't done that.
So it would just be like a regular sigma.
So those lone pairs end up in the drawing here. They're now in a sigma bond. Yep. And the chloro now has the electrons that used to be in a sigma bond, and now they're just a lone pair on chloro. So see, in this reaction, we're sort of trading. These electrons used to be in a bond, and now they're not. They're a lone pair. These electrons used to be in a lone pair, now they're not. They're in a bond. Yeah?
Can you explain again how the orbital is around the chlorine?
So the sigma star is on hydrogen and chlorine. It's on both of them. It's kind of like the pi star, which was spread out over the whole molecule, and it's in multiple places at once. No? Okay. Maybe let's draw HCl. There we go. All right, that's what the LUMO looks like. Here is the hydrogen in white, the chloro is in green. I'm going to just turn the LUMO on. You can see that most of the LUMO, and the red and the blue and the red simply mean areas of the wave function that are opposite in sign from each other. Every time you go from red to blue, you go through 0. Every time you go from blue to red, you also go through 0. And you can see that as you look, you can see there's nodes in between both of them. Hydrogen is here, chlorine is here. All of it is the same orbital. It just has different, it's the sigma star orbital is located in all of those places. So your question, all right, follow-up question? Sort of okay, maybe? All right. The reason the nucleophile attacks at the hydrogen instead of at the chlorine, because it could come over here and attack the chlorine. If it attacked at the chlorine, we'd form a new bond between the nucleophile and chlorine, and instead hydrogen would have the electrons. You're going to see real soon that H- is a way less better option than Cl-, because Cl is more electronegative than H. So Cl likes electrons more. Electrons are more stable on Cl than they are on hydrogen. So those are a couple of reasons why we attack the hydrogen. Yeah?
Can you go back to the orbital really quick?
Yep.
Does the smaller what's it called again?
At parts of the orbital, I call them lobes, like earlobes, I guess.
Smaller the lobe means it's more electronegative?
That's an interesting question. If the lobe is smaller, does it mean that atom's more electronegative? I think it might. I think that's a pretty good observation that probably holds. Yeah. Good question. At least for empty antibonding orbitals. All right. So an acidic bond between an electronegative atom and a hydrogen, that sigma star is an important place that can accept electrons from a nucleophile. You've already seen the pi star. There's a last one that I need to introduce to you. It's related to the one we just did, and that is sigma bonds between basically electronegative heteroatoms, and it's mostly, in this case, halides, but I'm going to include nitrogen and oxygen and carbon. Often have low energy sigma star antibonding orbitals. So an example of this might be the following molecule, which has a halide. Okay? And it turns out that carbon halide bonds, especially between carbon chloride, carbon bromide, and carbon iodide, those bonds are weak. They are especially weak. Weaker even than bonds between carbon and fluorine or carbon and carbon. When we say that a bond is weak, what we mean is that bond has a low energy sigma star antibonding orbital. Because of course, the way you can break a bond is either you promote an electron up to the antibonding orbital, or you take a nucleophile and you attack that antibonding orbital. So if the CBr bond is weak, that means the carbon bromide sigma star is low in energy. And that means it's likely the LUMO. The carbon bromide bond is especially weak. It is weaker than carbon-carbon or carbon-hydrogen sigma bonds. And that means that the carbon bromide sigma star is lower in energy than the carbon-carbon or carbon-hydrogen sigma star antibonding orbitals. Yes.
Is that just because on the stereotic table it's lower, so it's already filling up these inner shells? And so the carbon is translated or?
Yeah, that is a really great question, and actually a really good answer to that question. So why are carbon, bromide, chloride, and iodide bonds weak? The easiest way to explain it is just to know that chlorine, bromine, and iodine are a few rows down the table from carbon. They are therefore larger. They can't get as close to carbon. The bonds that are not as close are also weaker. Weaker bonds mean the bonding orbital isn't quite as low in energy and the antibonding orbital isn't very high in energy. So yeah, it's really the size of those atoms that makes those bonds weak. But do you understand the jump we're saying? A weak sigma bond has a low energy sigma star. Okay? And if the carbon-bromide bond is weaker than the carbon or carbon-hydrogen bond, then you would expect the carbon-bromide bond to sigma star to be the LUMO of the molecule. So let's just draw what that looks like. You will see that an antibonding orbital between carbon and bromine looks a lot like an antibonding orbital between between hydrogen and chloride. That is, on either side of this bond, you have tiny oppositely colored lobes that go through 0 in the middle. And then on the outside, on the carbon side and on the bromine side, you have larger lobes that are opposite in color, representing that there is a node at each of the nuclei. That's what a sigma star antibonding orbital looks like. It looks kind of like the opposite of a sigma bonding orbital. If you were to draw the carbon-bromine sigma bonding orbital, it would look like this, with a large lobe in between the two and tiny lobes on the outside, with lobes between the two with the lobe between the two having one wave function sign with no node, and the lobes on the outside having the opposite sign. So it's almost as though you took that bromide sigma bond and then flipped the orbitals out this way and put a node in between the two. This is the sigma star. Now, if we were to do a carbon-bromine bond in Spartan, let's just try that. I'm trying to figure out what this, no, I want to keep it simple. We'll just do methyl bromide. Oh, that is so not the right structure. There we go. So if you look at the LUMO, here, carbon is on the left, bromine is on the right. That's a long, weak carbon-bromine bond. If we draw the LUMO, you can see there's a node in between the carbon and the bromine, two smaller lobes facing each other, opposite in wave function sign. There's a node at carbon and a node at bromine, and you see this large lobe on carbon pointing away from bromine. There's also a large lobe on bromine. Now we're going to make the same analysis for the sigma star for carbon and bromine as we did for the sigma star for hydrogen and chloride. We're going to have to make a judgment call. Which atom is going to be the one that gets attacked? And the short answer is it's the carbon. If the nucleophile attacked the sigma star at the carbon, that breaks the carbon-bromine bond, and the electrons from the carbon-bromine bond go on to the bromine. So what you form is this new bond between your nucleophile and the carbon, and then bromine leaves with its electrons. These two electrons on bromine used to be in the carbon-bromine bond, sigma bond, now they're on bromine. Okay? The reason we do it that way, where the nucleophile attacks carbon instead of bromine, two reasons. First, the carbon nucleophile bond is stronger than the nucleophile bromine bond. And second, bromine is way better with an extra lone pair of electrons and a negative charge than carbon is. That's not immediately obvious to you now. It will become clear probably tomorrow. All right. But all of these satisfy the pattern of attack, identify the LUMO, nucleophile attacks the LUMO where the molecule's electron poor, and then we break a bond. All right? What you've seen here, and just to sort of zoom out and review what we've done, what we just did here is an example of a what's called a carbonyl addition reaction. We're going to do a lot of these, and there are going to be a lot of different nucleophiles and a lot of different carbonyls, but they're all going to follow that pattern. So now you understand the basic stuff that's going on in all carbonyl addition reactions. All right, second, what I've shown you here is an example of what I would call an acid-base reaction. Another way we'll call this is a deprotonation reaction, because the nucleophile is removing the proton from the acid. But in every deprotonation reaction, the nucleophile is dumping electrons into the sigma star on the hydrogen. And that's why you break the hydrogen, the bond between hydrogen and the chloride. Then lastly, with the reaction that I've shown you here, this is called a substitution reaction. Substitution. The reason it's called a substitution reaction is because we used to have bromo attached to the carbon. Now we substituted it out for the nucleophile. And because bromo leaves with its electrons in substitution reactions, we will often call the bromo a leaving group. Okay, with that in mind, you are now prepared to try question 1 from the quiz. These are 3 reactions. They're specific examples of the 3 things we've just talked about. The question wants you to circle the Lewis base and draw a square around the Lewis acid. The Lewis base is the nucleophile, or the molecule with the high energy lone pair electrons. Now it's not going to be immediately obvious which is which. So let me give you a hint. Start by looking for LUMOs that we've talked about. Look for low energy empty orbitals. Molecules with low energy empty orbitals will be the electrophile. So in that first example, I just showed you that the HCl sigma star is a low energy empty orbital. Oh, I guess I should just put it up because you guys have seen. There we go. I'm talking about this one. Oh, sorry. Before I go off on all of that, you can use the products to identify who is the nucleophile and who is the electrophile. Notice we start with HCl, then we end up with Cl minus. Where did the proton go? We formed a new bond between nitrogen and hydrogen. That's an example of a deprotonation reaction. Does that give you enough of a clue to get sorted on who's the nucleophile and who's the electrophile? Okay, go ahead and do that first one, and then we'll talk through it. Okay, I got no concept for how much time you need. Still need some time? Yes, please? Okay. Still need another minute? Okay, if you're finishing up, or if you're ready, go ahead and talk to somebody who's next to you, see if you've drawn same conclusions. All right, let's reconvene. I won't make any of you use the pencil of doom right now. That will come later today. All right, what do you think? Which one is, of just the top reaction, which one is the nucleophile? It's the one with the NH2 group? Okay, how can you tell that that was the case? It's got a lone pair, but what about chloro? Chloro's got lone pairs too. Well, HCl you know is an acid because it has the name hydrochloric acid, so acid is in its name. And if by association you remember that electrophiles are Lewis acids, the acid thing could get you thinking in the right direction. You were right, this is the nucleophile, which I said you're supposed to circle. But what if that didn't come to your mind? What else could you do to recognize the nucleophile? Go ahead.
You can't make any other bonds really. You can't add anything to that one on the left. You can't make any double bonds, and you can't add any on the left. That's
Right. There's no additional bonds you could make here. And somebody said look at the products, right? Tell me more about that.
Well, like if you just look at how the reaction ended up, you can tell that the amide at the beginning ends up having an extra hydrogen, and then the chlorine is wrong.
Right. This one gets a new bond.
Deduce what is happening.
Perfect. And chloro loses. Loses. Sometimes to troll my wife, I said in a text yesterday, "You're the best," Y-O-U-R, because it drives her nuts. It's Y-O-U apostrophe R-E. Loses a bond. Yes, a nucleophile is going to attack something and gain a bond. An electrophile, if the thing you attack is an antibonding orbital, the electrophile will have lost an old bond and gained a new one. Yeah.
Is the nucleophile that whole molecule or just the nitrogen?
Yeah, great question. Is the nucleophile the whole molecule or just the lone pairs on the nitrogen? And the answer is sure. It depends on your point of view. Yes, the whole molecule is the nucleophile. What is the nucleophilic or reactive portion of the molecule? It's the lone pairs on the nitrogen. Because you've identified right, we don't need to necessarily belabor that point. The HOMO is the lone pairs on the nitrogen, right? Okay, so that means this one, I'm supposed to draw a square. That's the electrophile, good. For the electrophile, look at the one, if the LUMO is the sigma star, look for something that loses an old bond but gains a new one. What's the LUMO on the HCl? Simply the HCl sigma star. Did you take a moment and draw that? Okay, I'm not going to do that here since we did it above. Or not above, but on the other thing. Check your drawing and see, does it look like that? If it doesn't, take a minute and correct your drawing. That's what a sigma star looks like. Yeah.
What's that Greek sign called again?
You don't need the deltas. The delta means partial positive charge and partial negative charge. Scientists use the Greek letter delta, lowercase Greek letter delta, to mean a tiny little bit of something.
Oh, we don't need that.
No,
Okay.
no, all just the gray outlines and the shading. Okay, questions about that? All right. I want to get started on a couple of these, but I don't think we'll have time to do them on a huge amount, or rather, I don't think we'll have time to spend a huge amount of time on them. And I think you're to the point where you could do a reasonable job on these on your own. So what I'll do is we'll get started, and then you can finish them, and I'll put the answers in the key. Mechanism. We forgot the arrow. Okay, for the what should I draw to show how this reaction happens? What arrows should I draw here? Go ahead.
Would you draw an arrow for the nitrogen and the
Yep, arrow.
bonds jumping onto the
Perfect. Yep, that's all you need. You need an arrow from the HOMO to the LUMO, and then you need an arrow with the aftermath of what happens to the LUMO. Okay? And this, all right, let's briefly talk through, we won't take the time, go ahead.
Sorry, could you explain what the little arrow is going to the CL?
The little arrow here represents what happens when you fill an antibonding orbital. The hydrogen chloride sigma bond breaks, and the electrons in that sigma bond go on to chloro. Yep. All right, yes?
So even though the arrow is pointing from nitrogen to the hydrogen, we see that it ends up being NH3. So that doesn't show direction of molecules necessarily, just the electrons?
The arrow, right. The arrow always shows only electron motion. I can't emphasize that point enough. This is something that people get mixed up all the time because they expect arrows to tell you where the atoms are going. Not so. Arrows only show electrons, only show the flow of electrons. You have to interpret the arrows correctly. How do you do that? Well, arrows must always start with electrons, either a lone pair or electrons in a bond. They never, ever, 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 world without end, ever start with atoms. You will be tempted to say, hey, look in this reaction, the hydrogen goes on to the nitrogen, so therefore the correct mechanism is that. And you're going to think, I understand that. Wrong. Don't do that. Okay? Arrows always start with electrons, either in a bond or on a lone or in a lone pair. They always point towards either nuclei or the space between two nuclei to indicate the formation of a bond. So notice the lone pair electrons on nitrogen point towards the hydrogen. That means they form a new bond with hydrogen. And if we were to draw out the full Lewis structure of that NH3 thing, we would see that the two electrons in this bond used to be that lone pair. That's what that arrow literally means. And this is why the arrows are important, because they show you how to draw the next step in the reaction. They show you how to draw the product. Now the arrow, the small arrow here, notice I started it with the sigma bond, and then it went to the chloro. That indicates the sigma bond is breaking, and the electrons in that sigma bond are going onto the chloro. In other words, if we say these electrons here in orange become become this lone pair on the chloro. Do you understand what the arrows mean? Yeah, go ahead.
Could you show what the arrows would look like for
The third example? Yeah, so let's show you what the arrows would look like for the third example. You might need to draw out the Lewis structure of the molecules so that it makes a little bit more sense. You at least need the carbon iodide bond. So, just real quickly looking at this third example, which one do you think is the nucleophile? The one with the oxygen. How do you know that? It's got a negative charge, so it looks electron rich. Nucleophiles are electron rich. They want to share electrons. So this one that's negatively charged, probably better nucleophile than the other one. So you're correct. If that is the nucleophile, what is the HOMO of that nucleophile? Easy, lone pairs on oxygen, no problem. Now, if this is the nucleophile, that means this, oh, and I'm supposed to, somebody should have said that's not a circle. There we go. That means this is the electrophile. If you didn't know that, look at the products. Notice that in the products, the oxygen is now bonded to a carbon. In fact, it's bonded to the carbon of a methyl group. And the iodide, which used to be in CH3I, is now over here, not bonded to anything. That's a clue. The oxygen is going to attack. It's going to make a new bond with carbon. And then the carbon iodide bond is going to break. Those details about what happens are important, but they're often difficult to memorize. We're going to, if we look at this reaction, you can see that we're going to make a new oxygen-carbon sigma bond, but we're going to break an old carbon iodide sigma bond. So when you get that, questions about how I looked at that? All right, so what's the LUMO on the electrophile? Yep, the carbon iodide sigma star. If we were to draw that, I'll take a moment just to draw it because this one is hard. There's a node in between the carbon and the iodide. There are small lobes facing that node, opposite wave function sign, and then pointing outward away from the space between the two nuclei, you have larger lobes on either side, and they have opposite colors. There's 3 nodes in this orbital, one at carbon, one in between carbon and iodide, one at iodide. We know from the product that the nucleophile, oxygen, attacks at carbon. So, and you can tell that just because you make a new carbon-oxygen bond. Where should my arrow start? Lone pair on what? Oxygen. Where am I going to point it to? Carbon. All right, if I stop there, I got 5 bonds to carbon, also, and so that breaks the octet rule, so that's a problem. But the fact that I dumped the electrons into a sigma star antibonding orbital, there's the star, tells me that I have to do what with that sigma bond? Break it. So what's my next arrow? Start with the bond, point towards iodide. This is how we show electron flow to explain how reactions happen. So we talked about the what. We make a new oxygen-carbon bond. We break an old carbon-iodide bond. This is another example of a substitution reaction. The arrows that we've drawn represent what's called mechanism. And mechanism tells you how. But the orbitals tell you why. High energy electrons on one molecule attack a low energy empty orbital on the other. Yes?
So how do we just have to memorize which orbitals work with which atoms, or?
Do we have to memorize which orbitals work with which atoms? What do you mean by that?
Like, so if you look at hydrogen, hydrochloric acid,
Yeah.
you have to remember the node, the 2 nodes, and then like, I guess the 1 node, and then the 2 lobes, and then the 7 nodes. How would we memorize like when you add, I don't know. Do you understand?
Okay, so I think the question is, you've noticed that a sigma star can have 2 different shapes. If it's a hydrogen something sigma star, it looks like what we drew above. If it's a sigma star between, say, two second row elements, it tends to look like this. Yeah, you need to be able to draw the two different kinds of sigma stars, and that's all there is. There's only those two kinds. Yeah.
So is it usually, does it just matter if it's between a hydrogen and a?
If it's between hydrogen and a second row element, the sigma star is going to look like this. If it's between two second row elements, the sigma star is going to look like that.
Okay, so it's only with the hydrogens.
Yeah. Okay, good. Other questions? Yeah.
Okay, so how do you know that the LUMO, the sigma star between carbon and hydrogen is, like, how do you know that it's not carbon?
Right, great question. So in this type of molecule, you've got 3 carbon-hydrogen bonds and 1 carbon iodide bond. How do you know which one? And the answer is you wouldn't. I could teach you some basic principles that would help you to know which bonds are going to be particularly weak, though that's probably best learned by experience. What I will tell you now is if I told you, and if you're able to remember, that carbon halide bonds are weak, whereas carbon hydrogen bonds are strong, that might help you. The weaker bond has the lower energy sigma star.
So is it because hydrogen bonds tend to be stronger?
Well, so bond strength has to do with a lot of things, but one of the easiest things is bond length. Hydrogen's small, it can get really close to carbon. Iodide, not so small, it can't quite get as close to carbon, so the bond is longer and weaker. And actually, if we go to Spartan again and look at, maybe I'll just draw, I wonder if it has this, I'll draw carbon iodide. What a horrible, there it is, okay. Compare the length of the carbon-hydrogen bonds there with the carbon-iodide bond. You see how much longer that is? Because it's longer, it's weaker. So there is a why. Generally, the iodide or bromide or chloride are so much larger than carbon that the bond has to be longer, and therefore it's weaker.
So as like a general rule, would you say it's most of the time the hydrogen bond is stronger?
Yeah, generally carbon-hydrogen bonds will be stronger than carbon-halide bonds. Good. Okay, so with that and with what we've talked about, I think you probably can answer this one in the middle. I'll clean this up for the key I show. You'll turn in your stuff at the end of class, but I will provide a blank copy of the quiz on the Learning Suite content page. I'll also provide a key, and you'll see a complete answer for this middle one here. I think you can do it because it's just an example of a carbonyl addition reaction. So if you have a hard time getting started, check your notes for carbonyl addition reactions. What we have learned is really, really important. Do you remember in Matthew 22 where someone comes tempting the Lord and asks him, Master, which is the great commandment in the law? And Jesus says, well, you shall love the Lord thy God with all thy heart, mind, and strength. The second is like unto it, love thy neighbor as thyself. We've just learned the first and great commandment of Ochem, which is homo attacks lumo. And the second is like unto it, nucleophile attacks electrophile. You don't know how to get started? Start with identifying the homo of the nucleophile and the LUMO of the electrophile. And if you can do that, then you can start drawing a mechanism. You'll be well on your way to predicting what's going to happen. Whew. Well, you need a break. We've gone too long. Take 5, and then we'll start back again.